Example 5 says, a pair of dice is tossed twice. What is the probability that the first roll is a sum of 7 and the second roll is the sum of 11? Again, I'm going to ask you to refer back to the chart that we created of the die on the previous page of this packet, where you look at all the sums. So what we need to do here is find the probability that the first roll is a 7, and we need to find the probability that the second roll is 11. Notice these rolls have nothing to do with each other. They're two complete separate rolls, so it doesn't matter what happened on the first and what happened on the second. So we're just going to take the probability of each of those, and then we're going to multiply those two numbers together. These are independent events. So if I look back at that chart, it seems to me the probability of getting a 7 was 6 of the 36 total possible, and the probability of getting 11 was 2 of the 36 total possible. When I multiply these two numbers together, go ahead and use your calculator and simplify. Let's see what you get. I'm getting a total of 1 over 108. Again, please put that answer in the answer blank. Looks like we just did this one on the previous page. If you listen to it, it says a coin is tossed 3 times. What is the probability that heads appears on all 3 tosses? So this was the probability of heads, heads, heads. But what this is saying is because what happens on the second toss doesn't matter what happens on the first toss, we can do these independently. So we can look at this as probability of heads times probability of heads times probability of heads, which in this case is 1/2 times 1/2 times 1/2. When we do that, we get 1/8. So let's look at some applications of conditional probability. One of these will be on the test. They are all set up pretty much the same. This is very, very important to understand for pharmacy, for a good example for pharmacy reasons. So let's take a look at this. I'm going to show you how to make it with a tree. You're going to construct all your trees the same. We'll do a couple examples together to make sure you understand this. Okay? So it says, suppose a company claims that a test has a 95% effective rate in determining whether an athlete is using a steroid. That is, if an athlete is using a steroid, the test is 95% positive, or positive 95% of the time. In the case of a negative result, the company says that the test is 97% accurate. That is, even if the athlete is not using steroids, it is possible that the test will be positive in 3% of the cases. Such occurrences is called a false positive. Suppose this test is given to a group of athletes in which 10% of the athletes are using steroids. What is the probability that a random chosen athlete actually uses steroids given that the athlete's test score is positive? So first of all, I hope you realize that it said, what is the probability given that? Okay, so when it says given that, we are not considering the whole set. We are only considering those athletes that tested positive. So if we want to find the probability here, what we're going to be looking at on the denominator is given, or we know that they tested positive. That's our denominator. And then on top, what we want is use steroids and tested positive. And I'll just put a positive here for saying and they tested positive. Okay, so before we start this and get into the numbers, I want to show you how we're going to break this up into every time. So the first thing that we're going to do is we're going to realize there's 2 types of people. There's those who use steroids and those who do not use steroids. So I'm going to call those no S. S and no S. For each one of those, we have an option of testing positive or testing negative. And I want you to think about each one of these cases in just a second. So let me finish drawing them out. Okay. So for instance, consider the first top branch. That would be someone who used steroids and tested positive. That would mean this is an accurate, good test. Let's look at the next one. Someone who uses steroids and tested negative. What is that called? That's called a false negative. That's really bad. This would be something like Lance Armstrong. When Lance Armstrong was biking and won all the Tour de France's and was testing negative even though he was using drugs, performance-enhancing drugs all those times. So false negatives are very, very bad things. Let's look at the next one. That would be someone who does not use steroids but tests positive. That's even more tragic in this case. That's called a false positive. They give a positive result, but it is false. They weren't actually positive. So think about an athlete who tested positive. They're immediately suspended, immediately given fines. Very, very dangerous for that athlete. And the truth of the matter is that they did not use steroids. So we want as few false positives as possible. The last branch is no steroids and negative. That would mean the test was accurate. So the only two branches where it's actually accurate is if they use steroids and it's positive, and if they don't use steroids and it's negative. The other false negatives and false positives are also very, very dangerous. Okay? So for instance, consider a different case. What if it was cancer and no cancer? Which would be worse, a false negative or a false positive? Well, honestly, you could make arguments for either. A false negative is very, very dangerous. That would be you had cancer, but the test told you you didn't have cancer. That's super dangerous because you're not getting the treatment that you need. The cancer could progress and it could be terminal. So you got to be very careful with false negatives in that case. That's probably the worst case scenario. Think about a false positive in the case of cancer. You have a test that says you do have cancer, but in actuality you don't. So yeah, you get the crud scared out of you because your test said you did possibly have cancer, but in the reality you're safe and fine because you don't have cancer. So a false positive in that case, it's scary, but not near as life-threatening as a false negative, which is the case that you had cancer and the test said negative. So each one of these problems are going to set up like this. It's going to be something like steroids, no steroids, positive, negative, positive, negative. So now let's start looking at this. It says, suppose that the company claims that it has a 95% effective in determining when an athlete is using a steroid. So what that's saying is, if they use steroids and it tests positive, that's 95% of the time. So if that's 95% of the time, that means... And actually, why don't I go back? Instead of writing these as percentages, I'm going to go ahead and use the decimal version of those. So I'm going to put 0.95 on that one. Okay? 95% positive. Well, that means that 5%, so 0.05, of those who use steroids, it says negative for. So it's not accurate. It gives false negatives 5% of the time. Let's consider reading. It says... in the case of negative results, the company says the test is 97% accurate. So if they don't use steroids, it'll say negative 97% of the time. Well, if that's 97% of the time it says negative, then that means 3% of the time we get a false positive. That's the really dangerous one on this one. Okay, let's keep on going. It says, suppose in the given test of athletes that 10% of the athletes are using steroids. So 10% are using steroids, which would tell us that the remaining, which is 90%, don't use steroids. So using this tree diagram, how can we get how many use steroids positive, how many use steroids negative, etc.? We just multiply the numbers. So how many use steroids and test positive? That would be 0.10 times 0.95. How many use steroids and test negative? That would be 0.10 times 0.05. No steroids and positive would be 0.90 times 0.03. No steroids and negative would be 0.90 times 0.97. Okay. So now we need to consider what the heck do we actually care about. We'll go back and read what was given. We were given that the athlete's test is positive, so that needs to be our bottom, our denominator. So how many tested positive? Well, there's no steroids who tested positive with this, which is that many. And then there's those who use steroids and tested positive, which is this many. So for the total who tested positive, we're going to have the 0.10 times 0.95, that's those who use steroids and tested positive, plus we have the ones who tested positive who did not use steroids, which was 0.90 times 0.03. Then on top, we just want those who use steroids and were positive. So those who use steroids and were positive was just the 0.10 times 0.95. So we'll put the 0.10 times 0.95 on top. Go ahead and throw this into your calculator. I'm actually going to write it as a percentage because all their numbers are in percentages. So for instance, I'm getting approximately 0.779. So I'll say that's about 77.9%, or I could have said about 78% on this problem. That's perfectly fine. So let's think about what the heck we just figured out. What we just figured out is if they tested positive, they have a 77.9% chance that they use steroids. That's what that says right there. If they tested positive, they have a 77.9% chance they tested positive. I want you to think the flip of that. The flip of that would mean if they tested positive, 22% of them, or about 2 out of every 10 or 1 out of every 5 people that this test says use steroids didn't actually use steroids. That's an alarming rate to me, because that, as an athlete, would kill your career. So the company is going to boast that it's 95% effective. Well, in reality, if it gets a positive result, it's only 77.9% effective. So what they're presenting to you is just one of the 4 possible options here. They're not trying to give you the truth of the matter, which is how much is it effective over the overall population. So very important you understand this problem. We'll do another example just like it right after this.